So here's a problem. Now this is one which looks a little bit wordy and intimidating. But you know what? We should learn not to be intimidated by things. We should learn to look at things and enjoy them for what they are. They're just trying to describe something. So here we go. Looking over the lab notes of an experiment, you're looking at the height of something, a certain object. It's given in meters at a given time, in seconds. So we can think of they gave us a grid here, which is very interesting. So our input we have is seconds, and our output we have is meters. All right. So we have this data, and we have some data, 2 data points. At 1 second, the height is 3 meters. So we can actually mark that. 1 second, height was 3 meters. And at 8 seconds, the height is 1 meter. Okay, 8 seconds, the height is 1 meter. Now you recall that you made one more observation, but you've lost the data in your notes. I hate it when that happens. But you do have some things that you recall. From the first observation to the missing observation, you have the average rate of change was equal to 1. From the second observation to the missing observation, the average rate of change was equal to -2. And the question is, when did you make that missing observation? Determine when that happened. But notice, there's an added fun. For added fun, little algebra. Okay, so our goal is we're going to answer this question. We're going to do it the fun way. And that's our goal, is little algebra as possible. Okay, well now, since our goal is as little as possible, let's shoot for 0. All right. We have something about average rate of change. Now, if you think about what average rate of change was, see, average rate of change, we can think of it geometrically. It's the slope. Because if I had a function, and I was looking at the average rate of change, if I have a point here and a point there, then the average rate of change was that slope of that data point. Or rather, the slope of the line that connected those 2 points together. So I'm told something. I'm told that there's this observation that was made, and the average rate of change was 1. So we can say, okay, well, what does that mean? It means that the slope was 1. So if I were to connect my missing observation to the first observation, I'd have to have slope of 1. Now, I don't know what my missing observation is, but I know how to draw a slope of 1. In fact, it's a nice 45 degrees. So that means if I come along here and I draw in a line through here, slope 1, the missing observation can happen anywhere, but it has to fall on the line. If it's not on this line, so if it's, for example, it's down here, slope is too small. Over here, slope would be too large. So wherever the missing observation had to occur, it had to occur on that line, slope of 1. Now that's just, of course, the first thing. We were told the second thing. Now the second thing says the following. It says, hey, if we go from the second observation to the missing observations, the average rate of change was equal to -2. Again, that's like a slope, -2. So now I go to that other observation, and I draw a slope of -2. And so the nice thing about -2 is it's a very convenient slope. Over 1, up 2. Now, what's the case? Whatever the missing observation was, it has to be on that line. Well, now the missing observation has to be on both lines. And we look at this and we say, you know, they intersect. And where they intersect, that had to be where the missing observation happened, because it's the only thing which is consistent with both facts. And so we go down and we see, lo and behold, the answer is 5. That's when it happened. So the answer is at 5 seconds. And I would say we achieved the goal, no algebra. So oftentimes it can be helpful to think about these things geometrically. Now you don't have to, but there's always a geometrical underpinning. Calculus is heavily built on geometry. So don't try to throw away your geometrical understanding of things. In fact, I would say keep it. Use it as much as you can. The algebra is great, but don't give up your geometrical thinking for algebra. On a side note, we can also say something else. We know when the observation happened. What else can we say? Yeah, we can also say what the observation was. We could have also said that, lo and behold, it was at a height of 7 meters at 5 seconds. All right. Well, continuing on, since we're beginning our math therapy sessions here, there's some suggestions for today. And we're going to maybe do one more of these after today. And the suggestion for today is don't focus on just procedure. Go beyond that. A lot of times you get the feeling if you sit in a calculus class, is like, well, there's like 20 rules and a half dozen procedures, and you just learn the procedures, and you do them without thinking. Now, that's not our goal. We don't want to produce people who can't think, who can only follow an algorithm. We want people who can do both. We want people who, yes, they can follow the steps, they can follow the procedures, but they know why the procedure works. Now, why is it important to understand why procedures work? Well, for one thing, it's a lot simpler to remember. If you understand why something works, then the rules make sense, and you don't have to go on blind faith. And oftentimes, you can get away with saying, okay, because I understand the process, I can actually just sort of give myself an outline to remember. I don't have to go into really fine details. The other thing is the second part, adaptability. So one of the things we like to do on problems, and you'll see this in quiz problems, you'll see this in old exam problems, maybe on new exam problems that you might get to see on an exam, is we take the procedure that you know and then we turn it upside down. So you say, okay, normally you start at the beginning and you're going to get an answer at the end. Now we're going to give you the end, and you have to tell us about something that happened at the beginning. Now, if you only know the procedure, it's not going to work. You're going to get stuck. But if you say, okay, wait, I understand the process, I modify it, life is good. So it's good to be able to understand things so you can be adaptable. And yes, this last point, it does make it more enjoyable. I know the words enjoyable and math are not often put together, but I do think you can have fun. Yeah, the problems are challenging, but you can enjoy doing the math. So I hope you enjoy the class. All right. So where were we? Well, last time we had this picture. We said, we really care about flat things. And our most important flat thing is our tangent lines. So I have my function, this sort of upside down curve here. And I'm interested in this tangent line. It's shown here in red. And I say, look, that's the most important line, that tangent line. Now the problem is it's hard to find a tangent line because you only get 1 point. And when you do with lines, you really want 2 points. 2 points. So the 1 point is where it's tangent, or it touches. So the good news is you can get secant lines pretty easily. Now secant lines, you cross. So you cross it, and you hit it at 2 or more points. So what you can do is say, look, I can pick 2 points, form a secant line, which is an approximation to the tangent line. Sometimes it's a very bad approximation. But it's an approximation. So oftentimes that's where you start. You approximate. Well, how do you get better? The way we get better is we move the other point closer. So as we move that second point closer, our lines start to become more and more like our tangent lines. So we say, all right, so we have this idea. Now, we're interested in the slope because that's measuring the rate of change. So we say, look, the slope of the secant line is f of b minus f of a over b minus a. I want to get closer and closer. Well, here's a solution. Let's put in b equals a. Can't get any closer than that. Well, why not do that? 0 over 0. All right. 0. All right. Now, this leads us to a question. We should understand the answer to this question. So here's the question. It leads us to 0 over 0. The question is, why is that bad? And you're probably thinking, because I was told that by my algebra teacher, and they were my favorite teacher in high school, so I know it's bad. I can't divide by 0. But why? I think it's important to understand the why. Because if you understand the why, then you understand how to start fixing the problem. And once we understand how to fix it, we get to understand the process that's going to underlie the foundation of calculus. So we start by just a simple observation. We say, look, A divided by B equals C is true if I can take A and write it as B times C. That seems like a very reasonable statement to make. You know, if you thought of these as fractions, you're like, oh yeah, I just multiply both sides by B. So I can say 6 divided by 2 is equal to 3 because 6 is 2 times 3. All right. So now what happens if we have B equals to 0? Well, if I have A over 0 equals C, well, that has to be that A is equal to 0 times C, but 0 is a magical number. One of the best numbers. In fact, I would say it's the best one. If you were ranking numbers, 0 comes in the first slot. And of course, if you're a computer scientist, you'd say 0 comes in the 0 slot, so that's even better. The next number is after 0 is 1. But yeah, 0 is beautiful. And the reason it's beautiful is 0 times anything is 0. Now there's two possibilities here, and I want to make sure we understand the difference. So what's one possibility? Well, one possibility is that A is not 0. And now we run into a problem. Because A can't both be 0 and 0. Because a number is something. It's not somehow simultaneously two different things. So if A is not 0, it's just flat out can't be done. But there's another possibility. A could be 0. So when A is 0, it does satisfy that constraint here. It satisfies the condition that A equals 0. So now the question is, what's bad about 0 over 0? Where's the catch? The problem here is not that this relationship isn't satisfied. The problem becomes, what is C? It turns out that anything you chose for C would still work. 5 times 0, 100 times 0, negative 21 times 0. All of these are valid choices to the relationship 0 times C. So you can't get an answer because there's not one single choice that satisfies the result. So the problem is ambiguity. You run into ambiguity. Okay. So now we know our problem. Division by 0 is bad because either what we have is impossible or it's ambiguous. So now we say, okay, how do we solve this? Well, since we don't know what 0 over 0 is, because it could be anything, instead of asking the question, what is it? We've changed our question ever so slightly and ask, what should it be? Now what we mean by that is we say, well, oftentimes when we get to our 0 over 0 expression, it comes from something happening. So let me be a little bit more clear if we come back to our picture for a moment. When we plug in b equals a, we get 0 over 0. Both the numerator and the denominator would be the same. But we can think of it as b getting closer to a. So in other words, as b gets close to a, so there's sort of this processing happening. There's something, one value is approaching another value. So we can say, as things are getting close, what's the behavior? So this is where the limits come in. Limits answer the question, what should happen? So we have a notation here. Limit as x goes to a. So this is our variable. The x part is what's varying. And so we have x is varying, but it's varying and it's getting closer to a of the expression f of x, which depends on what x is equal to L. So as x gets close to our value a, our expression f of x gets close to L. Now, when you hear the words close, what that means is it's sort of secret code. So close means a distance. There's a small distance, and the distance is getting smaller and smaller. So some of you might remember that there was a sort of a technical definition of the limit. And it said the following. You said that the limit as x goes to a of f of x equals L if for any, oh, this is the fun stuff, epsilon greater than 0, there is a delta greater than 0. So if 0 is less than x minus a less than delta, then absolute value of f of x minus L is less than epsilon. The good news is we don't do this definition. So, but it's good to see it. It's good to see it. If you've seen it before, here's the way you interpret it. X gets close to A. Well, close is a measurement of how far you are. And the way you measure something in terms of distance is absolute value. So x gets close to A is that part. The distance between x and A is the absolute value of x minus A. And we're saying it's small. That's our saying, look, there's some small choice of delta. So I'm close to A. Then f of x gets close to L. So there's a second notion of closeness. The second notion of closeness is here. F of x minus L, that's how far away you are from the function in L. That can be small. And again, you can see that there's a second distance there. So it's really talking about how things get close to one another and as we move on. All right, but for right now, it's going to suffice for our purposes just to have the intuition that says when x is close to A, f of x is close to L. There are some technical issues, and we will, from time to time, dip our toe into the technical issues, but the intuition is solid. Now, there's one thing to keep in mind, which is why things get very interesting, and it's the following. What should happen is not always the same as what does happen. So in other words, you can get two different answers. You can say, well, what should this be? And then you can ask, well, what actually happened? Now, when they're the same answer, we think that's a nice thing, and we actually have a special name for that. We're going to talk about that next week. But it might be the case that they disagree. And of course, it might be the case that you don't know what does happen, which is how you use this information to fill in the gap. So here's an example. Suppose I have the following function. F of x is the following. It is either x squared plus 3x minus 10 divided by x minus 2 if x is not 2, or if x is 2, it's 1. Okay. So this is piecewise, meaning that we define it in different places using different rules. So we can answer some questions. What is f of 2? Well, we plug 2 into our function. We see that when x equals 2, we're in the second rule. And according to the rule, what is f of 2? It's 1. So f of 2 equals 1. Now we can talk about the second part. So now we want to know, well, what's happening to the function as we get close to 1? Well, in this case, we say, okay, we have the limit as x goes to 2 of f of x. Now, the key here is that when we're talking about limits as x gets close to 2, our intuition should be we're nearby 2, but not at 2. Because limits only care about what happens nearby, not what happens at our value. So, if we're not at 2, which rule do we need to use? Yeah, the top one, the first one. So, this becomes the limit as x approaches 2 of x squared plus 3x minus 10 over x minus 2. Now, our natural intuition here is, well, we could plug in 2 at this point and just see what happens. It turns out that that's a good thing to try. If you try it right now, what you would get is downstairs you definitely would get 0. Upstairs you'd get 4 plus 6 minus 10, which means you get 0. So right now it looks like it's getting to 0 over 0. Now when you see 0 over 0, the mindset is, aha, that means we get to do more work. Yeah. All right, good. Well, so we should think about what's happening. Now, oftentimes when you have a 0 over 0, that's a signal that there's something causing a 0. Now, it's easy to see that there's something causing a 0 downstairs, that x minus 2 is causing a 0. But that must mean there's also something upstairs causing it. So let's think about what we can do. Is there another way to rewrite x squared plus 3x minus 10? Yeah, x minus 2 times x plus 5. In fact, we should go into there completely confident that it's going to factor. And not only are we going to be completely confident it's going to factor, we can be completely confident that one of the factors is x minus 2. And the reason we can do that is because we know 2 is a solution. If 2 is a solution, x minus 2 has to be a factor of the polynomial. All right. What is the tempting thing right now for us to do? The thing we're like, ooh, I think we should do this. Yeah, the tempting thing is to cross out x minus 2. Now, the thing that we're going to do is we're going to cross out the x minus 2's. All right. But we're going to be smart. And we said, you know what? We were smart in that we didn't lose any information. Because there's always a thing you have to be ever so slightly careful about. When you cancel, you have to make sure that what you cancel is not 0. Are we okay? How do we know that x minus 2 is not 0? Because x does not equal 2. X does not equal 2. Remember, the limit says don't look at the point, look near the point. And so we're away from 2, so we're okay. There wasn't a chance that we somehow canceled zeros. So good. All right, so we now have that this is the limit as x approaches 2 of x plus 5. And now we say, okay, so what's happening right now is we could have rewritten our expression, and it says the rule is to whatever you plug in, add 5. Okay, so if what we're plugging in is getting close to 2, and we add 5 to it, what's the result getting close to? 7. Essentially, we plug in x equals 2, and we get 7. Now, here's the comparison. F of 2 is 1. The limit as x goes to 2 of f of x is 7. And it turns out, this is a true thing, they're not the same number. 1 and 7 disagree. So this is a case where there's sort of a disagreement going on. If you were to sketch what this looks like, what's happening is you have something that looks like the following. You have this function, but there's a hole, and somehow that hole got moved down. And we're going to talk more about these types of issues and problems. We'll give names to everything later on. Okay, so there's an example. Okay, let's do another one. This is a very famous function. So let g of x equal sine of 1 over x if x is not 0. And be 0 if x equals 0. And I see I have a typo here I haven't fixed yet. What is g of 0? Because there's no f here. All right, well, that's pretty easy. What is g of 0? It's 0. Yeah, because the rule says if you plug in 0, you get 0. Now, the fun part. So we're looking at the limit as x goes to 0 of g of x. Again, because we're not at 0, we can say that's the limit as x goes to 0 of sine of 1 over x. Now the question becomes, what happens to sine? Well, let's recall what sine looks like. So if we sketch the sine function, we see the following. So let's just sketch sine first. So we'll draw some grids, and then sine does the following. It goes up and down. And in fact, you could say it goes up and down in a sinusoidal fashion, which is another way of saying it looks like a sine curve. It goes up and down. All right, now this is sine of x. But what do we want? We want to say, what happens to sine of 1 over x? What is that 1 over x really doing to us? Well, one way to think about what's happening, let's think about it in the following way. What happens to 1 over x as x goes to 0? Ignore the sign for a second. What happens to 1 over x as x gets close to 0? It gets big, right? Now it can get big positively if x is a little bit bigger than 0. It can get big negative if x is a little bit less than 0. Okay, so what happens to the sine function as x gets big? So as I keep going, if I were to keep drawing, off the screen now, but if I were to keep doing that, what's happening to the sine function? It keeps going up and down. Sine function will keep going up and down forever, over and over again. Now here's the crazy thing. That 1 over x is trying to say, all this stuff that's happening way over here off towards infinity, we're going to take that part and squeeze it in near the origin. So what's the effect? Well, if we draw our axes here, so another way to think about it is what's happening to sine 1 over x way off towards infinity. Well, towards infinity, 1 over x is close to 0. So sine is very small. And then, as I come off from infinity, I start to go up and down. But then I start to go up and down faster, and faster, and faster. And it starts to look like that. So the infinitely many oscillations that are going to be over here get squeezed into this little tiny spot, and this sort of little bit of an oscillation here pretty much is like everything. The 1 over x flipped it. All right. So that's what sine 1 over x looks like. What does it do? So what happens as x gets close to 0 of sine 1 over x? By the way, I didn't draw the picture on the other side, but it looks the same. There's a lot of ink here. I have a small ink budget. Okay. So what's happening to sine 1 over x as I get close to 0? What is it doing? What value is it approaching?
0.
Is it approaching 0? Yeah, I guess you could say it's approaching 0. Is it doing anything else? It's oscillating. So does it approach one value? No. See, that's the thing, is as I move closer towards 0, it's going to keep going up and down. And so any value between -1 and 1, I'm going to be able to get close to that value where x is very small. Okay, so I'm not going to one value. I'm actually going to a range of values. But limits say, look, I have to say a limit exists if I approach a single number. This isn't approaching a single number. So what's the conclusion? The conclusion is this limit does not exist. So limit does not exist. It's not going to one single thing. So the moral here is that limits cannot exist in all sorts of interesting ways. And we've barely begun to scratch the surface. We'll do a lot more of this in the next week or so. So there are some nice rules. Here are some basic properties of limits. Now, some limits are super easy to understand. So for instance, suppose I have c as a constant. And I want to say, suppose my variable x is getting close to a. What happens to my constant? The answer is, it's a constant. It doesn't change. That's, constant is this sort of idea of non-changing. So because it doesn't depend on x, it's always going to be the same. And so we get that the limit of a constant is the constant value. Now the second statement here looks more sophisticated until you say it out loud. So this says, as x gets close to a, x gets close to a, which everybody agrees on. As x gets close to a, x gets close to a, that's the second statement. Okay, so that's great. Now the rest of these sound pretty straightforward, and they're not so bad, but they're not trivial. So I don't want you to say, oh, these are all just easy to do. Some of these will take lots of detailed proofs, and if you love detailed proofs about calculus, we have many wonderful courses. In fact, there's even a whole major on campus set aside for talking about detailed proofs about calculus. They call it the math major. It's a great major. So if you want more information, you can go take more classes. But right now, we have a couple of intuitive things. The first one says that limits are what are called linear, which is it's really easy to work with scaling, which is multiplying by a constant, and addition. So you can break up over addition, and you can pull out constants. So if I have f and g, and I'm assuming that those limits exist, then I can break them up and do the limits individually. If the limits exist and I'm multiplying them together, I can multiply the limits. So limits work with multiplication. Now, you have to be a little bit careful here about what your assumptions are, and we'll point this out at the bottom. There's a warning here. Division works as long as your denominator is not going to 0. Now, if your denominator goes to 0, there are sort of two possibilities. Now, one possibility is that your numerator went to a non-zero number. And at that point, you say, okay, limit does not exist. Or you can go and be a little bit more refined and say, well, it's like getting arbitrarily large, or positive, arbitrarily large, negative. But the other possibility is it's going to 0 over 0. And when you see 0 over 0, what does that mean? More work is correct. When you see 0 over 0, more work. So things get interesting. Also, we have exponentiation. So if I have a function to a power, then I can basically say, well, look, if I want to take the limit, I can put the limit inside the exponentiation problem. So in other words, limits behave in a very nice way, and we're going to see properties of these later on. Now, a lot of these statements here, there's this base assumption that says, suppose your limits exist. And that does not show up very brightly. But imagine I had boxed this part right here. Suppose the limits exist, then it's very easy to combine them together and find the new limits. However, it is also the case that the limits may not exist individually, but you can have it so that their product exists, or maybe their sum exists, or some other combination. So be careful. Just because the limits don't exist doesn't mean when you combine them together that the limit still does not exist. Interesting things can happen. For example, on next week's quiz problems, you might see examples of that. So we want to start with sort of a really nice base set of expressions to work with. And using our fact that limits work really well with addition and exponents, we can get that there's one particular class which is very nice, and that is polynomials. Polynomials are nice. Beautiful to work with. Now, what's a polynomial? Essentially, a polynomial is a linear combination, which means we're just adding things together with some numbers in front of powers of x. And we're thinking of x to like whole numbers. So x cubed, x squared, x to the 21. So because of where polynomials come from, they come from constants and x's, and then we add and multiply those things together, or we say, hey, wait a second, we know about the limits of constants, we know about the limits of just x, so what we can do is now we get the following. If I want to say, well, what's the limit as x goes to a of f of x? Well, what we can say is, all right, f of x is a polynomial. Now, I can use the fact that limits respect addition, and I can pull out constants. That was the word linear. Okay, so that says I can break up my limit as the sum of a bunch of little limits. And now I say, hey, you know, each one of these little limits is something we can do. In fact, what we can do is instead of thinking it says x to a power, I'll think of it as a limit and have that limit to a power. So I can pull out the exponents. And now each one of the limits that are left is a very simple limit, and so I can evaluate. So polynomials are beautiful functions. They have the following amazing property, that the limit as x goes to a of f of x is f of a. No surprises. That's great. We don't want too many surprises. That's hard to work with. All right. As it says there, what should happen is what does happen. Now, once you have polynomials, it's not hard to talk about rational functions. So a rational function is anywhere where you have a polynomial over a polynomial. And it can be the case that suppose you have a rational function, polynomial over polynomial. If the bottom part doesn't go to 0, then you just plug in, and life is good. All right, well, some simple examples. Maybe they're simple. Find the limit of the following polynomials and rational functions. Okay, so, let's start with an x. What do you want x to go to? 4. All right, what polynomial do you want? 5x squared. Let's make it interesting. E to the pi. All right, what's the answer? Well, first off, is this a polynomial? You might say, well, no. There's an e to the pi there. That's an exponential. Or is it? Is e to the pi exponential? No, it's not. What is it? It's a constant. And I know you're like, wait, I thought constants had to be like nice numbers, 5 and 17. No, constants can be, for lack of a better word, ugly. But they're still constant. And treat them like constants. Okay, so the rule says this is a polynomial. So in the limit, what we expect to happen, that's the limit, is what does happen. Okay, so to take the limit, just plug in 4. So 5 times 4 squared plus e to the pi. And there we go. Done. Okay. Well, these are going to be quick, I suspect. All right, let's try another one. Suppose we change t goes to 2. Okay, so now we're not going to use x as a variable, we're going to use t. Okay, we need a polynomial. What do you want? What? 4t cubed. 4t cubed. Okay, we can have more. We can also not have more. Plus 18? 8t. Oh, 8t. Okay. All right, that's sufficient. All right, 4t cubed plus 8t. Now, question. So far we've talked about what happens as x gets close to something. Now we've switched gears. Now we're saying, what happens as t gets close to something? Oh my gosh, are we in trouble? No. It's the name. And one of the things we got to get used to is the idea that it doesn't matter what name we use, it's about a process. And names can be changed to suit our purposes. So in our case, we're going to switch x to t. It's the same philosophies in play. So what do? Well, plug in 2. It's okay that there's no t squared. It's okay there's no constant. You don't have to have all the values in. So let's see, that would be 4 times 2 cubed plus 8 times 2. And if we weren't told to simplify, that would be great. If we wanted to simplify, we could also say this is 48. But we weren't told that we had to simplify. So we're fine. All right, well, let's try another one. Okay, theta goes to pi. All right, in the interest of time, 5 theta squared. Ooh, how confusing should I be? Very? I like that, thank you. Plus x over theta plus 2 pi. This is not very confusing, I hope. Okay, so there's the limit. Now, there's a couple things different. We've changed our variable name again. There's theta. We've also changed to a rational function. But the rational function, we say, look, just try the same thing. Plug it in and see what happens. Let's talk about downstairs. What do we get? 3 pi. We are ecstatic when we see 3 pi, because what's true about 3 pi? It's not 0. And it's like, it's not 0. We're done. Whoa. Okay, good. So we're going to get an answer. This is good. Okay. What do we get upstairs? 5 pi squared. But what about the x? What does the x become? See, right now it's x, and now the x is going to become x. Yes. This is a case where x now represents something we don't know, but it's not the thing that's varying. What's varying right now? It's the theta that's varying. And so we just treated x like, well, it's something, we'll leave it as x for now. We will see problems from time to time this semester where it's like, well, we have some things which are varying and some things which are staying put. Just treat whatever's not varying, treat it like you would any constant. So we can leave our answer as 5 pi squared plus x over 3 pi. That's okay. That's okay. Are you convinced you need more? No, you're not convinced? Oh man, I thought I was pretty convincing. Well, okay. Do another one on later on. We want to make sure we get through the next slide. The best slide. The wonderful slide. Okay. All right. So much to do on this one. So the challenge comes from what happens when you have 0 over 0. When we don't have 0 over 0, we're pretty comfortable with that. And we're going to talk more about cases where we don't get 0 over 0 next week. But what happens when we do get 0 over 0? Well, there's a variety of approaches. And so we're not going to do all of them today. There's a beautiful idea coming up next time. But I want to mention 3 ideas. And we're going to go through and practice. So there's 3 examples coming up. The first thing is, suppose you have something which involves a polynomial. If you have a polynomial, what can happen is, if it's the 0 coming from the polynomial, that means there's a root of that polynomial. Factor that polynomial out and grab that thing that's causing a 0. See, what's the idea here? The idea is something caused our 0. And if something caused our 0, if we can just figure out how to get that thing that causes 0 and get something else that causes a 0 downstairs and say, lo and behold, these things are going to cancel each other, then life is good. So factoring can be a way to isolate the zeros. What's the thing that's causing the zeros? Now, another thing that comes from algebra is the conjugate. So when you hear the word multiplied by the conjugate, it's just a fun way of saying flip the sign in the middle, whatever the middle part means. This comes from the following fact. If you take a plus b times a minus b, and you multiply them together, you get a squared minus b squared. Now, right now you're saying, okay, well, why is that useful? Well, let's see, I have some more bullet points here. It's useful because you might have a square root. See, the way to get rid of a square root is to square something, but you can't just I'm going to square everything, because that's not allowed. You have to do algebraic rules that you're able to use. Squaring everything is not a rule that you can do. But you can do things by multiplying by the conjugate that helps you work with the square root. We'll see an example in a few minutes. Now, when you multiply by the conjugate, you're multiplying by something. We always have to make sure whatever we do, we don't change the problem. Now, there's 2 things that you can do to any problem that won't change what you're doing. One thing you can do is you can always add 0, because it turns out 0 has another beautiful property. If you add 0, you don't change anything. The other thing is you can multiply by 1. So if you're going to use multiplication to work with an expression, make sure if you multiply the top, you multiply the bottom, because that's multiplying by 1, and you're okay. The last thing is look for trig identities. And one of the most important ones, of course, is sine squared plus cosine squared equals 1. You're not going to need any obscure trig identities. These are all going to be basic trig identities. All right, so let's do some examples. Limit as t goes to a half. 2t squared plus 5t minus 3 divided by the quantity t plus 2 squared minus t minus 3 squared. Now, if you plugged in a half and were very patient, you would discover that the numerator turns out to be 0. On the other hand, the denominator turns out to be 0. So it's a 0 over 0. I'm going to skip that step, but you can check it if you want. I believe that t equals a half causes 0 in both upstairs and downstairs. So what do? We do more work. Oh, good. Someone's got it. Yeah, okay. We do more work. So we can factor. Now, the upstairs, okay, does the upstairs factor? And we know before we start that, yes, it's going to factor. But do you see how it factors? This one's a little bit more interesting because there's a 2 here. Oftentimes, we only have to deal with like a t squared. So because 1/2 is a solution, here's the quick check. It's 2 times a fourth, that's a half. 5 times a half is 5 halves. A half plus 5 halves is 6 halves, which is 3. Then we subtract 3. So 1/2 is a root. So that tells us that if I have a polynomial, t minus a half is a root. But oftentimes we like to work with polynomials that don't have fractions. So instead of t minus a half, we'll say, well, 2t minus 1 will be a root. Because that's a nice expression. T equals a half would be 0. So if I were to factor the numerator, I could say, hey, this becomes 2t minus 1 times something else. But now that I know that it has to be 2t minus 1 times something else, so something else is not hard to figure out. So for instance, I got the 2t squared. What should go in the start? T, because I need to get up to 2t squared. 2t times t is 2t squared. I have a minus 3. What needs to go at the back end? Plus 3. And if you multiply that out, you'll get 2t squared plus 6t minus t, which gives us 5t, and minus 3. Okay, that's the upstairs. Now, how do we handle the downstairs? There's 2 different things we can do. And they both work. I'll let you pick. Option 1. Well, expand the 2 polynomials out, combine them together. Option 2, be a little bit sneaky. And use the fact that we have a square minus a square. They're about the same amount of work. Here we go. I'll just make a little note. If this is a, and this is b, and I say, hey, look, it's a squared minus b squared. So this becomes a plus b, t plus 2 plus t minus 3, times a minus b. Yes? A plus b, a minus b. Now, in the start, there'll be t plus 2. You can imagine putting parentheses here. When in doubt, put lots of parentheses. T plus 2 plus t minus 3 becomes 2t minus 1. Ooh, that's very convenient. Here, you get t plus 2 minus t minus 3. The t's would cancel. And be really careful to lose the sign. Minus minus makes plus, so b times 5. And that's what the second term would be. So, what happens? Well, because we factored, we figured out that the things which were causing our zeros were these 2t minus 1 terms. We can cancel those. And what's left is we have a t plus 3 and a 5. So this becomes a limit, as t goes to 1/2, of t plus 3 over 5. And now it's a rational function. It's an equivalent rational function when I'm away from a half. But now I can just plug in a half. Because if I plug in a half, what's true about the denominator? It's not 0. It's 5. So 5.5 plus 3, giving us, of course, 7/10. All right. Well, there's 2 other ways, 2 other problems. Let's skip to the last problem, because that one's pretty quick. Sine squared over 1 minus cosine theta. Sine of 0 is 0. Cosine of 0 is 1. Get 0 over 0. Well, okay, so we want to cancel. Well, what can we do with sine squared? Trig identity. What's another way to write sine squared? 1 minus cosine squared. Now, what's true about 1 minus cosine squared? So 1 minus cosine squared is 1 squared minus cosine squared. It's a difference of squares. So if I have a difference of squares, I can factor. So this becomes the limit, as theta goes to 0, of 1 minus cosine theta, a minus b, 1 plus cosine theta, a plus b, and then downstairs 1 minus cosine theta. And now what can we do? We can cancel off the 1 minus cosine thetas. So we get the limit as theta goes to 0 of 1 plus cosine theta. And what does happen to cosine theta as we get close to 0? What does cosine approach? Goes to 1. So our answer is 2. Time to finish this last one, and this is going to be a good one. So we've done the expanding and factoring polynomials. We've done using the trig identities. Now we're going to do the multiply by the conjugate. And we see this, it's useful for dealing with square roots, because we see that we can square something. So here we have this example. We have the limit as y goes to 3, square root of y plus 1 minus 2, square root of y plus 6 minus 3. Now if you plug in 3, that can give you sort of an idea of what should happen, because these are reasonable functions on top and bottom. Upstairs, it looks like square root of 4 minus 2. Well, that's 0. Downstairs, it looks like square root of 9 minus 3, which is 0. 0 over 0. And when you see something like 0 over 0, that's a sign. It's a sign that we need to do more work. More work is about to come. All right, so what do we do here? Well, we'd really like to get rid of one of these square roots. In fact, we'd like to get rid of both of these square roots. Our goal is to remove the square roots and be left with something that we can cancel out. So how do we do that? Well, we have here the sort of the a minus b. So suppose I want to get rid of the square root upstairs. So I'm going to multiply that by the square root of y plus 1 plus 2. Now if we did that, we're in good shape. Okay, but what do we need to do downstairs? Well, now it's a different expression. So we'll multiply by square root y plus 6 plus 3. Now, of course, we can't just multiply by this particular form, because if we did, we wouldn't be multiplying by 1. So we're going to have some other terms. So we're going to have a square root of y plus 1 plus 2 and a square root of y plus 6 plus 3. So net effect, since those are the same and those are the same, we're multiplying by 1. Life is good. Life is good. Now, one of the things you might see is that when you're multiplying this out, there's a question. What do you multiply and what do you not? So the rule of thumb is expand out that something if it's going to be useful to expand. Otherwise, don't expand it. Don't multiply it out. Because oftentimes when you multiply it out, you sort of lose information. You don't see how things really fit together. So what do I mean by this? So for this particular problem, I would say we want to be multiplying the two terms here together and multiplying these two terms together, but we're going to leave these terms separate on the ends. So if we do that, what do we get? Well, square root of y plus 1 squared is going to become y plus 1, and then we have minus 2 squared minus 4. Downstairs, square root of y plus 6 squared, that's y plus 6, and then we're going to have minus 9. All right, that's the first part, and then we have this other part. Y plus 6 plus 3, square root of y plus 1 plus 2. And again, the limit is the whole thing here. Now looking at this, what do we see? We see a y plus 1 minus 4. That's really y minus 3. Y plus 6 minus 9. Well, that's also a y minus 3. So what happens is these two terms cancel. So we see that we can rewrite our original limit using some algebra as the limit as y goes to 3, square root y plus 6 plus 3 over square root y plus 1 plus 2. Now, before we got 0 over 0, bad. What do we get now? Well, now when we plug in 3, 3 plus 6, 9, square root of 9 is 3. And then plus 3 more, which means the top is going to 6. downstairs, square root of 3 plus 1, square root of 4, plus 2 makes 4. So 6/4 or 3/2. All right, and there you go. There's the limit. So, none of these are particularly hard. It's just a matter of practice. Now, we are sort of looking at these in isolation, but keep in mind, it can be interesting when we start to see these ideas merge together. So don't think that, there's only one idea. Oftentimes, there's a variety of ideas. And you say, all right, what's the tool I need now? All right, that allows me to update. Good. Now I have a slightly different form. All right, now what do we do? Well, we work that problem. Okay, and then what? Well, we update, and we keep working. Work the problem. Just keep moving it a little bit closer, and then, when it's just close enough, boom, done. Life is good.